We can start, Frank.
Okay. So it is a pleasure for me to introduce this first mirror conference between CIRM and IMPA. And we will start with the first speaker today, who will be Carolina Araujo in Brazil. So far we cannot see Carolina, so I hope we can see her soon. Hello, Carolina.
Hello.
So Carolina will talk about regular foliations. I don't see on algebraic surfaces. So please, Carolina.
Thank you, Frank. Thank you, Jorge. So first of all, thanks for the invitation. It's a pleasure to give a mini course in this first mirror event between IMPA and CIRM. So I chose to talk about regular foliations on algebraic surfaces. So I come from algebraic geometry, and really I think this is the best that I could talk about, is to tell you a little bit about algebraic geometry, more specifically birational geometry, with this motivation in mind. So the main reference for this mini course is going to be this paper by Brunella from 1997, which is called Holomorphic Foliations over Compact Complex Surfaces. So this is the goal. The goal is of this mini course is the following. So we are going to be working in the following setup. So S will always be going to be a complex projective non-singular surface. And we are going to be considering F well, in principle, possibly a singular holomorphic foliation on S. And what we want to do is to classify pairs of a surface together with the foliation under the condition that F is a regular foliation. So there's no singular points. So this was achieved in this paper of Brunella, and the idea of this mini course is to explain some ideas that appear in this paper. So let me start by discussing some very easy examples of regular foliations on algebraic surfaces. So possibly the simplest example is the example given by, say, ruled surfaces. So here I start with any C compact curve and E a rank 2 vector bundle on C. And we consider the surface S is going to be the projectivization of this vector bundle. So this comes with a P1 bundle structure. This gives a P1 bundle structure on S. And we could take the foliation F to be induced by this P1 bundle structure. So this example is going to show up a few times in this course. So let me just maybe mention that conversely, if you start with any P1 bundle over a curve, it is of this form, the projectivization of a vector bundle. This vector bundle is not uniquely determined by the surface. You can twist it by any line bundle. But this is it. So for instance, if So if C is P1, then up to twisting, we can always take the vector bundle to be a direct sum of P1 with some twist for some positive, non-negative number n. And then in this case, the projectivization of E is what we call the Hirzebruch surface Fn. And geometrically, you can realize it as follows. So F naught is just P1 cross P1. F1 can be seen as the blow up of P2 in a point. So if you blow up the point, you replace this point by all its tangent directions, and then this F1 will then admit a fibration to P1. And for all others Fn's, you have a similar picture. For higher values of n, what you can do is you can embed P1 inside a projective space Pn by the Veronese embedding. And then, so this is the image of P1 under the Veronese embedding. And then on Pn plus 1, you can take the cone over this curve. And now if you blow up the point, the vertex of the cone, what you get is exactly a ruled surface. And this is exactly the Fn that I described in this way. Okay, so these are exactly the ruled surfaces, but this can be more generally we can consider what we call regular fibrations. So if you start with any, you can start with any dominant morphism from S to let's say to B. So B here is a smooth curve, smooth projective curve. And here I take a morphism with connected fibers. So if this morphism will induce a foliation on S, if and only if, so if I want it to be really maybe a regular foliation, sorry, this is a regular foliation on S, that is a foliation without any singular points, then for this to happen, this happens if and only if the only singular fibers, of course, if F is a smooth fibration, this will induce a regular foliation. But it is possible that F is not smooth, but it still induces a foliation. And this happens when the singular fibers are multiple with a reduced structure. So this happens if and only if the singular fibers of F are multiple with non-singular reduced structure. And these are, so this is what we call a regular fibration. So this is different than not necessarily smooth, but with this condition. And these are basically all the foliations that have regular foliations with algebraic leaves. Now, you can also have plenty of foliations with with dense leaves. And let me just give you one example here. A simple example is if you take S, an abelian surface. So this means that S is the quotient of C2 by a suitable lattice and then in this case, of course, on C2, we can consider the foliation, a foliation given by parallel lines, with a certain, let me take lines with a certain slope, say yx equals lambda, and it translates. And then when I look at the quotient, this will induce a foliation on the abelian surface, which is called the linear foliation. So this will induce a linear foliation on the quotient. So these are some simple examples of regular foliations on surface. And now I would like to give some non-examples, so that we try to understand how special or how rare are these foliations are. So for this, so before I can give you some non-examples, let's look at the foliations from a different point of view. So if F is a foliation on a surface S, so S for me will always denote a smooth projective surface. So this foliation can be viewed as we can look. This is going to be described by an exact sequence of sheaves on S if given in the following way. So on the tangent bundle of S, for every point, you can look at the tangent space of the foliation. So this will give us what we call the tangent bundle of the foliation. And this is not necessarily, in general, for a possibly singular foliation, this is not going to be a subbundle, this is just a subsheaf, but we can always saturate it so that the quotient here will be the ideal sheaf of some subscheme of length 0, at most 0, tensored by a line bundle and F. So any foliation on S can be described by an exact sequence like this. So here, TF and NF are line bundles on S. And either Z is empty, so this is what we call a regular foliation, or its length is 0. So in this case, the singular set of the foliation is exactly the support of this subscheme, which is a finite set of points. Okay, so this is how I am going to look at foliations. So for instance, if we reinterpret our goal from this point of view, what we want to classify now is so the goal is to classify surfaces S together with line bundles TF, such that, well, when I look at this exact sequence here, this gives me two ways to describe my foliation. I can describe it either by considering this subsheaf, and in this case, what we have is that, so this gives us that this foliation is defined either by a global section of this vector bundle. So this vector bundle, the dual of the tangent bundle, we usually will denote by KF, the canonical bundle of the foliation. So, and then, or I can, if I dualize this sequence, I can represent my foliation as a non-zero section of, here, the sheaf of Kähler differentials twisted by, then here we're going to get the normal bundle. So these are the two usual ways that we look at a foliation on a curve. On a surface, it can be either locally given by a vector field, and this is what this is telling us, or it can be given by locally by a one form, and so this is exactly what we have here. So if you want, and then in this case here, the singular set is precisely the zero, the singular set of F. In this case here, this is going to be given by the zeros of this, the zeros of this section. And in this description here, this will be given by the zeros of this one form. So they have isolated zeros, and the zeros correspond to the singular locus. So if you want this to be regular, then this is going to be empty. And then in this case, it's telling us that the second, so that this section here does not vanish anywhere. So if you give your foliation by a twisted vector field, in order for it to be regular, this vector field cannot vanish anywhere. And from the point of view of algebraic geometry, we express this in terms of Chern classes, and this is exactly telling us that the second Chern class of this vector bundle, for instance, TS twisted by, let me call this KF, is zero. So this is as an algebraic geometry, this is what I want to classify. And then using basic properties of intersection numbers, let me rewrite this as, I can rewrite this as the C2 of TS, which you usually call the second Chern class of the surface, plus C1 of TS dot KF plus KF squared. Okay, so this is in particular, this must, for a surface to admit a foliation, I must be able to find a line bundle for which this is non-zero. So let me just state this. So this is usually called, so let me write this as a proposition. So these are called usually the Baumbach formulas. So if F is a regular foliation on S, then that second Chern class must vanish. So first part, so this is just what I just said, that the second Chern class of S plus C1 of S Kf plus Kf squared is equal to 0. So this is the first formula. We can change it slightly. What we could use the fact that, so let me go here to the formula. So from this formula here, from this exact sequence, we see that the first Chern class of S can be written as Tf, or the first Chern class of Tf plus the first Chern class of Nf. And so we may, if we want, we may use this to rewrite this as minus, so this is minus C minus, let me write it, Kf dot Nf. So this is what is called the first Baumbach formula. There is another one that is also very useful that we are going to use, is that when you have a regular foliation on a surface, then the normal bundle has 0 squared. So here I'm using all the time the intersection theory on the surface, and I often identify the visors with their associated line bundles. I hope this will not be confusing. But with this formula, we can already give a few non-examples. So the first non-example that I want to discuss is P2. So P2 does not admit a regular foliation. And this is just because if I have a regular foliation on P2, again, this would correspond to, let me view it as a section of a vector bundle of a twisted, a global section of the twisted sheaf of Kähler differentials, so times the normal bundle. So I have a section, a non-zero section here. Now, if we use the second Baumbach formula, this is going to tell us that this line bundle that appears here, it should have self-intersection 0, but on P2, if I have a vector bundle who's with self-intersection 0, we will imply that this is just the trivial line bundle. And so I would get a section of the sheaf of differential forms on P2, but we know, for instance, from the Euler sequence that this has no global section, so this is 0. So for instance, if you look at the Euler sequence, so here we have So if you look at the Euler sequence, you see that this vector bundle cannot have any global section. So P2 cannot admit any regular foliations, but this is not special only of P2. Let me also discuss another important class of projective surfaces, which are K3 surfaces. So a K3 surface is a projective surface for which, so what I want is that the canonical divisor on S is trivial, so that in other words, the sheaf of two differentials is isomorphic to the trivial sheaf. And I also want that what we call the irregularity of S, so this is just the H1 of S OS, or by Hodge duality, the H naught of omega S, this is 0. So this is a very important class of surfaces, and we will show that such a surface does not admit regular foliations. And again, this follows from these two formulas. So if you combine them, you will see that this implies that the second Chern class of the surface is just the product of Ks and F. And now for, actually this is just, this is just what this is just this interpretation here that I wrote here. So if you look at this inequality here, this cannot hold for K3 surfaces. So for K3 surface, the second Chern class is always positive. It is always 24, I guess. 24, while this number is always 0. So in this case here, C2 is always 24, while C1 Ks is just 0. And so this again violates the Bound-Bott formula. So these are some non-examples, and the idea is that what we want to do is to now give a complete classification. So maybe my purpose today is to state the classification result, and then tomorrow we are going to start to look at some tools to prove this. But the idea will be to exploit these two line bundles, the tangent and the normal bundle of the foliation, and their numerical properties and effectivity properties in order to get this classification. So before I start into further discussing the properties of these line bundles, I would like at this point to revise the classification, the birational classification of complex projective surfaces. So what is the goal of this, a birational classification. So in general, and this is for any dimension, what we want to do in algebraic geometry is to, given a projective variety, find a simplest representative of this variety in its birational class, and then try to somehow classify this distinguished, simpler models. So to make this precise, let me just give a definition. So we say that a surface is minimal. So here, for me, a surface is always a non-singular projective surface. It is called a minimal surface if any birational morphism from S to S prime, and this is this S prime here is, as before, is again a non-singular projective surface. So any birational morphism of this type is an isomorphism. And this is the special model that we want to find in any given birational class. And now here is a fact from surface theory. Whenever you have, and this is definitely not true in higher dimensions, but very useful for the theory of surfaces, whenever you have such a morphism, a birational morphism between two non-singular projective surfaces, this can be decomposed into finitely many blow-ups. So F can be, F is a composition of finitely many, of a finite sequence of blow-ups, blow-ups of points. So let me just remind you, we are going to use a lot blow-ups. So let me just remind you and fix some notation. So let me review the blow-up. So if you start with any surface S and a point on S, the blow-up of the point is going to be, again, a non-singular projective surface S prime with the property that, so with a birational morphism to S, which is an isomorphism outside of P, and replace the P by its a P1 of, so this E is just the inverse image of the point. And this is isomorphic to P1 and has self-intersection -1. So this is the general for any surface and any point you can construct, you can take the blow up. And so we see that if a surface S tilde is the blow up of some other surface, it must contain a curve with these properties. So let me. And a curve with these properties is what we called a -1 curve on the surface S. And it is a classical theorem from the Italian school, Castelnuovo's contractibility theory, that says that conversely, if you find any -1 curve on your surface, this -1 curve can be realized as the exceptional curve of a blow-up. So Castelnuovo contractibility theorem says that conversely, any -1 curve is the exceptional curve of a blow-up. And so, as a corollary, what we see is that a surface is minimal if and only if it does not contain any -1 curves. So this is how we get what we call a minimal model for a given surface S. You start with S, and then you ask, does S contain -1 curves? And if the answer is no, then you stop. And you have a minimal model, a minimal surface. If the answer is yes, well, then you pick such a -1 curve, so you can realize it as the blow-up of some other curve, S prime. And here is your curve here, lies as the exceptional over a point. Then you can consider the contraction, and then you go back to the beginning with S prime replaced by S. And then you ask again if S prime contains -1 curves, and you go around, and at some point you have to stop because you see that, for instance, the Picard number of S drops at every step. So this is what we call the minimal model program in dimension 2. So this is a way, an algorithm for you to start in with a surface, find a simplest representative in its birational class. Okay, so this is the first step. Now we know how to find a simplest representative in a birational class. And now what we want to do is to classify these minimal models, the minimal surfaces that appear in this way. And this is what is known as the Enriquez-Kodaira classification. So it gives a list, in a sense, a list of the possible minimal models. So in order to write this list, I have to introduce some birational invariants. Of non-singular projective surfaces S. And so here are some of them. So let me define some of this. Some invariants of S are birational, others are not. For instance, the second Chern class or the first Chern class squared. So these are integers that in general are not birational invariants. So now let me define some numbers that are birational invariant. So the first one is the genus of the surface. And this can be defined as the H naught of the sheaf of two forms on S. We also have the irregularity QS, which can be defined as before. I have already mentioned this. This is just the this number, or by Hodge duality, this one. And also the one that is going to be particularly important for this classification is what we call the Kodaira dimension. Which we all often denote by kappa S. So let me define it in a slightly more general way. So if I start with D, any divisor on S, I can look at its the linear system defined by D and then consider the map induced by this linear system. More generally, let me do this for any multiple of n that contains sections. So let me first define the semigroup of D. So this is the semigroup of non-negative integers such that so I want to have sections of n times D. So this is ND. I want this to be non-zero. And then whenever I have a n here, I can consider the rational map induced by this linear system. This goes to some projective space. And so this map, the image of this map will have some dimension, and the Kodaira dimension of K, in general, the Ithaka dimension of D is kappa D. This is going to be we say that it is minus infinity if the semigroup is trivial. And otherwise, I can consider the maximal dimension of these rational maps. So I take this maximal of the dimension of the image of these rational maps. Here for M in ND. So this is the case when this is non-trivial. So if I define then the Kodaira dimension of the surface to be the Kodaira dimension of the canonical class of the surface. So this is any divisor on S such that whose associated sheaf is just the sheaf of two forms on X. So this is this Kodaira dimension, then it will be either minus infinity or 0 or 1 and 2. And the Kodaira, Enrique's Kodaira classification can be written in terms of these three invariants. So let me quickly state it. So here is the Enrique's Kodaira classification. So those with Kodaira dimension negative, these are precisely the this is P2. So this is S is either P2 or ruled surfaces. So these are the ones that the first example that we considered. And here we just have to remove except F1, because F1, as we saw, this is just the blow up of P2 in one point. In particular, it's not minimal, but the minimal ones are P2 and all other ruled surfaces. Then you have also the classification of surfaces with Kodaira dimension 0. And here there are 4 basic classes. So we have, so now the classes, we are going to distinguish them by looking at other invariants, the genus and the irregularity. So there is the case when the genus is, and the irregularity are both 0. So these are called usually Enriquez surfaces. There is the case when the genus is 0 and the irregularity is 1. So these are called bielliptic surfaces. And they have a very well described structure by, as you can imagine, by elliptic fibrations. Then you have the case that we have already encountered where the genus is 1. So you do have a global section and Ks is 0. So this is exactly the case of a K3 surface. And then you have the case when the genus is 1 and the irregularity is 2. And these are, again, the case that we have encountered, abelian surfaces. So this is the case of Kodaira dimension 0. Then there is the case when the Kodaira dimension is 1. So these are what we call elliptic surfaces. So they admit a fibration whose general fiber is an elliptic curve. So this is an elliptic, what we call an elliptic fibration. And then finally, there is the case of Kodaira dimension, the maximal Kodaira dimension. And these are called the surfaces of general type. And they are called general type because actually most surfaces will lie in this class, and in general we cannot say much about them. So this is the Enriquez-Kodaira classification, and now I want to state the Brunella classification of regular foliations on surfaces. So it says that if you have a pair SF, where S is a non-singular projective surface and F is a regular foliation on S, then they must be of one of the following types. So it could be that F is induced by a fibration. So this was the first examples that we saw. Another possibility is that F is completely everywhere transverse to a fibration. So F is not induced by a fibration on S, but S admits a fibration which is everywhere transversal to F. So F is everywhere transverse to a fibration. And notice that this case here is very special. Not only we have the Baumbach formulas that give us restrictions on the invariance of F and T, but this transverse structure says that this fibration on S has to be isotrivial. So this is really a locally trivial fibration, and this is given by the intersection with the foliation being transverse. So in other words, this, if I have such fibration from S to B, this is just given by a representation of the fundamental group of B in the automorphism group of the general fiber. So this is, again, the structure is completely given by this group homomorphism. Then there is another case that we have already encountered, that F is a linear foliation on an abelian surface. Now, comes another case that we have not yet discussed, which is the case of what we call a turbulent foliation. F is a turbulent foliation on an elliptic fibration. So what this means, let me just draw a picture. So in this case, we have that our S admits a fibration to a base B. And in this case, turbulent means that, so this is an elliptic fibration. So the general fiber is an elliptic curve. And moreover, except for some finitely many fibers, so there are some special fibers that are tangent to the foliation. So these are invariant by the foliation. And so the foliation has these fibers as leaves, and then outside these fibers, it's everywhere transverse. So this is what we call a turbulent foliation. And then finally, there is the last class, which in a sense corresponds to the surfaces of general type, which is, again, this only happens for surfaces of general type. And what we call here, I'm not going to say much about this, I think João Paulo will discuss this in the last class. F is a transversely hyperbolic foliation. So this is a very special structure, and then which is going to be discussed in the last class. So today, this is what I wanted to tell you, to explain to you what is the theorem. And let me just say a few words of what we're going to do in the idea of the proof by Brunella is the following. At least, maybe let me divide in two cases. So if you look at the Enriquez Kodaira classification, if you look at the cases where the Kodaira dimension is at most 1, in almost all these cases, your surface will admit either a rational fibration or an elliptic fibration. There are some exceptions here. There is P2, and here there is, abelian surfaces also. Well, here we know that there is no regular foliation, but also for abelian surfaces, they may not have any fibration, but all the other ones admit either a rational or elliptic fibration, and the idea of the proof is going to be compare our given foliation F with this fibration. And this will show that either the F is induced by this fibration, or we will, by comparing them, we will see that it must lie in one of these three cases. In the case of foliations on an abelian surface, then there may not be any fibration to compare, but we also have a linear foliation with which we can compare the given foliation. And then in this case here of surfaces of general type, then we have to follow, in general, they will not have a fibration, and so we will have to look at this from a different point of view. So tomorrow I will try to give you some ideas of this, the first part of the proof, how to explore a fibration, and then the last class we move to Kodaira dimension 2. Thank you.
Thank you.
Okay, thank you, Carolina. We have time for quick questions. Anyone here? Anyone in at CIRM? Do we have questions in either side of the Atlantic?
Yes.
Are the several classes in the theorem of Brunella disjoint?
Here, no, sorry, I should have said that, thank you. No, they're not mutually disjoint. You can have, several of these conditions can be satisfied at the same time.
Another question?
Does the behavior for K3 surfaces generalizes for hyperkähler manifolds, or is this special to the surface case?
So for this, so I have not looked at hyperkähler. Okay, so I have not. This is an interesting question. I have not looked into that, and I have not really thought about this for in higher dimensions. But maybe it's a good topic for the discussion session.
Thank you. Is there some question on the other side of the ocean?
It doesn't seem so, Frank. So I propose that we resume in 6 minutes, or 5 minutes and 40 seconds, with the Remy talk. Does it sound good for you?
Yes.
Perfect. So 11:05, we will be back.